Hey guys, this is a quick demo of my project to build an electric-driven turbocharger compressor. I'm not exactly sure what I'm going to use it for yet, but I think it's going to be a fun project. Let me just give you a quick demo of what it can do right now. Currently it's just driven by a vacuum cleaner motor as a quick test. So I was initially going to show you the 500 watt run here, but I figured I may as well go out and show you the 6 kilowatt run. Wow, that's powerful. Yeah, so that draws about 12 amps at 66 volts DC. That's about as much voltage I can give this vacuum cleaner motor without overloading it. Yeah, these are not very efficient at all. There's something like maybe 75%, so dissipating a couple of hundred watts. So this is basically a turbocharger compressor off of, I believe it was a 14-liter Cummins marine diesel. The compressor wheel actually looks like this. I got this whole turbocharger quite a while back to build a turbine, I think about over 10 years ago, and then ended up giving up on the project, so I figured I'd use the parts to actually do something. Yeah, so this gets the compressor wheel up to about 10,000 RPM with this motor. From what I can remember, I seem to have lost the spec sheet, but this is rated, I think about 70,000 RPM and will produce about 50 PSI of boost on the output, but I don't know if I have any hope of getting it quite to that speed. It'll take pretty much the entire output of a car engine, about 150 horsepower, to drive it to that speed. So to make this, I've had to machine a large block of aluminum on the lathe to act as sort of a bearing block. This replaces this piece that came with the original turbo. Also had to machine a custom shaft for the turbo mounts on, because this shaft, the hole in the compressor wheel is very some weird size, not any standard metric or imperial value, something like 14.3 millimeters or something. Yeah, the outside output is just a standard half-inch shaft. I just put some shaft couplers onto the vacuum cleaner motor. I had to add a fan to it because these motors are normally cooled by the output from the blower that they're driving, and that normally the air flows through the motor to cool it. But yeah, this was required to get enough cooling. The purpose of this test is to determine or get a ballpark figure of how much power is required to drive this compressor. In this case, I measured this to go at about 10,100 RPM with the current setup. And to get the mechanical power, we're going to do a little bit of a trick to get an approximation of the mechanical output of the motor based on the electrical input. And basic procedure there is to take the electrical input power and subtract off the IR losses inside the motor. So to do that, we need to get the resistance. So let me just restart this meter that turned itself off. We will lock up the rotor carefully, and I've set the power supply current limit to the current we were running at, 12 amps. So we'll just measure the voltage across the motor under that condition. So 12 amps at about 23 volts. And as it warms up, the voltage increases because the resistance of the wire increases. So now we can determine approximately how much power is lost in the IR drop of the motor, and that'll allow us to get an approximation of mechanical output. The actual output will be lower than that because this is not taking into account friction or other losses like eddy current in the laminations. So looking at the numbers here, we have 23 volts at 12 amps stall, 67 volts at 12 amps operating. So in this case we can just subtract the stall voltage from the operating voltage. We get 44 volts at 12 amps, which is 528 watts. So we'll call that 500 watts output because there's other losses we're not taking into consideration. And for a fan like this, assuming an incompressible fluid, the power is proportional to the RPM cubed, and the pressure is proportional to the RPM squared. So I was thinking of using 2 electric ducted fan motors from RC airplanes, rated 6 kilowatts. They look something like this. I was going to use 2 of these in line with shaft couplers. These turn at about the right speed, about 30,000 RPM, so that's about 12 kilowatts total. And doing a bit of math, if 500 watts takes us to 10,000 RPM, we'll need about 12 kilowatts to take it to about just under 30,000 RPM. And if we're getting 9.5 inches of water pressure at this speed, based on this formula, we'll get about 3.5 psi output at 29,300 RPM. So, if we assume that these equations hold for compressible fluid, we'd get about 164 kilowatts to drive this compressor up to 70,000 RPM. That's about, what, 220, 230 horsepower, something like that? Yeah, I've been looking at this. I couldn't find any easily available information on this, because basically as the air is compressed as it's flung outward due to centripetal force, it's going to increase in density, so that would basically increase the amount of power required to drive this. However, it also decreases in volume, so yeah, I'm unsure if these equations hold at higher, for compressible fluids at high pressure. So if anyone has information on that or can point me to a reference or textbook or something, please do. These numbers also give you an indication of why those electric turbochargers you buy for your car are completely useless. Like this, for example, this running at 12 kilowatts would produce about 3.3 psi, and that's actually enough boost to produce a usable performance gain in a typical engine. And I believe this system would produce probably about the right amount of air to go with that amount of boost into a car engine. But you're taking 12 kilowatts, which is going to be about 1,000 amps drawn from your 12-volt battery, which is just completely impractical. So that's why those electric turbochargers will never practically do anything for your car. So I was going to end the video right there and wait for the new motors to come in, but I had a look around the shop, and I was playing around with these large outrunners that I had got for an electric bike project a while back, and figured it might be relatively easy to modify them to drive this, and actually it was. Yeah, both the motor and the tooth belt pulleys I had here were from an electric bike project that I sort of ran out of time or gave up on, but they're just about perfect for driving this. We've got about 2.8 to 1 gear up ratio. This spins at something like 7,000, 8,000 RPM, so that's should be just about right to get the compressor up to a pretty good speed. So let's give this thing a try, and let's see, number 1, if the tooth belt holds out, and number 2, if the bearings hold out, because there's going to be quite a bit of side load on this. This motor is connected to a Hobbywing 160 amp 14S ESC, which is connected down to my bank of 6 battery chargers, which produce 60 volts at about 135 amps max. Okay, let's see what this thing does. So far so good. That's nowhere near maximum power though. Okay, that's actually sounding very smooth. I'm going to get a current meter on that and maybe a RPM meter so we can see how fast it's going. the nozzle is about to blow off. I'm going to have to reinforce that a bit. But yeah, we got it up to about 75 amps. I'm not sure what speed yet. Let's see approximately how much thrust this generates by putting this scale in front of the discharge. So that was about 2.6 kilograms. Pretty good. So I just gave this a run at 60 amps, so 3.6 kilowatts for about 2 or 3 minutes, and yeah, the motor is getting very hot. Here's a thermal image of the motor itself. The windings are getting to about 130 some degrees Celsius. The motor controller is staying very cool with this fan on it now. Let me figure out what the RPM was at that setting. So according to the high-speed camera, at 3.6 kilowatts input power, 60 amps, this turns at 20,900 RPM. Let's try bringing it up to full power, 100 amps DC. That's 6 kilowatts input, which is exactly what that Outrunner motor is rated for. So that got the fan, or the compressor, to 22,300 RPM at 6 kilowatts input. Let's go check what pressure that produced. So about 2.7 psi or so. Okay, wow, that is insanely powerful. Okay, full power. We're going to give it all these supplies can give, which is about 130 amps. So about 115 amps was max. So I think that's pretty much all I can do on this for today. I came up with this setup with a couple of vacuum cleaner motors blowing on the motors, and that allows us to operate this pretty much continuously at 100 amps, although the motor still gets really hot, about 140 degrees Celsius winding temperature. So numbers from this are 60 volts, 60 amps, so 3.6 kilowatts at 20,900 RPM with about 1 psi boost. and 6 kilowatts gets us 22,300 RPM with 1.7 psi boost. So that's pretty much in the ballpark of what I was expecting, but this motor gets really, really hot when running at 100 amps. I have a suspicion that the efficiency is much lower as the power goes up. So yeah, I'm still going to order in those EDF motors and have them directly drive the compressor. I was actually thinking of putting them on the intake so that they're in the airstream so they get good cooling. Anyway, this concludes part 1 of this video. Thanks for watching.